Hello. A few weeks ago I bought one of these SD card readers, micro SD card readers, for something rather unrelated to what this video is going to be about. So I just checked that it worked and then I put it aside and kind of got distracted with other things. But then today I received a couple of other things in the mail which made me think of using this SD card again, and they are, if I can just get them in here. This is a laser diode, I think it is, and it just sort of turns a laser on and off. It's a laser pointer basically. And this over here is a receiver, and you can point the laser at that, and when it detects that the laser is pointing at it, it'll give you a high signal on here for your Arduino to read. Very, very simple to use, and I was very surprised at the effectiveness of this. I managed to transfer data at 115 kilobits per second from about 20 meters away, at least. I haven't checked further than 20 meters, but I know that at least it works 20 meters away. And the data that I was transmitting was just a bunch of numbers, so I just had a byte and I was counting it up and then letting it overflow and just sending that sort of rather meaningless data. But there was enough to see that it worked. But I thought it might be interesting to try that data connection with some more meaningful content. So that gave me the idea to try something else that I've been sort of thinking I'd have a go at recently, and that is trying to get some audio to play from an Arduino. So that's where the SD card comes in, because we can put lots and lots of data on here and the Arduino can read it in quite quickly, quick enough to play audio. And yeah, so that's what I'm going to do in this first video, and then I think I'll make another video to show how you can use these two things as a data transmission connection. Anyway, so in this video we're going to look at the SD card and the audio. So what have we got to have a look at here? I have some pages. Oh yeah, this is the page, or this is where I got it from, Banggood. Pretty cheap. You get 3 of them for $3.50, $3.48. So yeah, not much of a cost outlay there, and they're also very, very easy to use. I actually, when I got it, I thought I might make a video about using it, but it turns out it's just so easy it's not really worth making a video on. So the library that I'm using is the official, I guess you could say, Arduino supplied. I think it was supplied with the Arduino ID, I'm not sure, because I've got so many libraries from other places these days that I can't remember where they all came from. But this is the one. These are the examples that I have, and I'm going to look at card info and dump file in a minute. So that's where they come from. If you don't have them, you can probably find them on Arduino's main website. And those pages are for the audio stuff. So let's just open up my Arduino IDE, and I'll yeah, like I said, whoops, I think this is included with the Arduino IDE, at least on my examples menu here. Put it on screen so you can see it. In the examples menu, if I go down the bottom, you probably can't see it, but there's SD, and then in that sub menu I'm going to select card info. So that'll bring us up this card info sketch, and I'll just put that there. And I will check that we've got this in the right place. Arduino Uno, yep. So what this is going to do is it's just going to show us a little bit of information about the card that we have in there, I think. Yes, we have one in, okay. So I'll just upload that, and when it uploads, we'll see what the serial monitor says. Now I noticed that there's a couple of problems right off the bat in this library, which I was a little bit surprised about actually, because it's at least I think it's the official one that's supplied with the IDE. But the problem that we're having here is the connections. We should look at the connections first, shouldn't we? Let's do that. That doesn't take long. If you are familiar with SPI, you should be familiar with what we're looking at here. We just have ground and VCC, and then we have the 4 SPI pins. Very simple stuff. And I'm using ground and VCC there. This is just a regular Arduino Uno R3, but it's just sort of different color and different maker and stuff. And then over here I'm using pins 10, 11, 12 and 13 for the standard hardware SPI. So that's the connections. And the problem, if we go back to here, the problem is that the chip select pin is not matching. And the strange thing is that if you look in the source code here, it says chip select equals 4, and then somewhere down here we're using 10. So I'm not sure what's going on here, but I just set this to 10 because that's what I'm using. And then if we try that again, we should see some more useful information. So this is just a dump showing you what, type of volume you're looking at and the size and everything. So it's it's supposed to be 4 gigabytes micro SD card, and it has these files on here, which these ones here are actually invisible when you're looking at it through most file explorers. So it's interesting that it shows them up on here. And then we have this thing here, fade mono. This is my audio file that I have prepared earlier, and that's about 3.7 megabytes, sorry. And then we have a file called test.txt, and then another file here. Notice that they have this tilde in the name. It seems that you can only use the FAT32 file system with this stuff, and that means that all your file names are going to be the standard 8 characters and then 3 character extensions. So you can't do any of those long file names that we have so commonly now, but it used to be that you couldn't do that on old DOS operating systems. So I think you're going to have to call your file names by 8 characters and then a 3 character extension. Otherwise, actually I'm not sure if it might just rename it itself with this tilde thing in there to make it shorter. Anyway, so we have this file here, and I'm just going to look at this test.txt file to start with, and we'll just dump the contents of that file to the serial monitor using the other sketch that is in the examples. So now I'm going to go down to SD, and I'm going to select dump file, which gives me this one. And again, I have to change the chip select to whichever chip select that I'm using, which is 10. Connections are all the same. And now let's have a little bit of a look at the source code here, because I never really bothered to look into the details of this too much. It's pretty simple. You have a begin. It's almost like the serial connection, really. You have a begin, and then you have an open to specify which file you want. I think you can go with uppercase or lowercase, which is another side effect of having this FAT32 or the old style namings. It doesn't matter. There's no case sensitivity in the file names. So I'll just try that with lowercase for my file name. And then once you have a file opened, you do a very similar thing to what you do with software serial and that kind of connections, where you just check if there's something available and then call read on it to get the next byte from that file. And after a while, this available function will return false, and then you can exit the loop. So that's what this loop is doing here. And then I suppose you should close the file, because it says only one file can be opened at a time. So it's just something to keep in mind if you're doing more complex stuff. And just to be pedantic, the error should say that. All right, so let's see what happens when we upload that. Okay, this is a text file. That is the text contents that I put into that test.txt file. So we can see that the dump file is working correctly. It's finding the file on the micro SD card, and it's just reading out each byte in the file and dumping them to the serial monitor for us to look at. Now, in the case of my music file, I don't want to dump it to the serial monitor to look at. I want to send it to some speakers, and the way you can do that, we end up with a pretty horrendous sounding music file because we have to reduce the bit rate and the quality of it down so much. But let's have a look at how I've managed to do that. And one page that was really helpful when I was doing this was this page here on instructables.com. If you search for Arduino audio output, you'll find this pretty quickly. And this is where I discovered a thing called a resistor ladder, or an R2R converter, or digital to analog converter. And the reason it's called a ladder is probably quite obvious from the way it looks there. But this lets us take an 8-byte number. So you can see there's 8 wires. So if you imagine that each one of these wires is representing 1 bit of an 8-bit number. So that's a number from 0 to 255 in value. And they're being connected into these consecutive pins on the Arduino. And this just happens to align with a certain port. And I'll have a look at what ports are in a minute too, just in case people are not aware what they are. But they're quite handy for doing writing of digital pins very quickly. So just imagine that each one of these pins on here is 1 bit of an 8-bit number. The way these resistors work, I don't totally understand this, but if we look at the which one should we look at? Let's look at this one. So you can do this with as many bits as you need, but we're only looking at 8 in this case. So the reason it's called an R2R converter is because you use 2 values of resistance, and there'll be whatever R is, and then there'll be twice as much as R. And the way they're laid out somehow or other causes this is where I don't really follow too closely how it works, but basically you get an analog value out here which represents the value of what these bits would be in a digital number. So you'd have the most significant bit here, I think, and then the least significant bit there, closest to ground. I think that's how it works. So anyway, so the R and the 2R, the 2R should be twice as high resistance as the R, and in this particular case, the person making this instructable has recommended 10K and 20K resistors for this ladder. I don't have enough 10K resistors around anymore to do this because I've used them all as pull-up or pull-down resistors for other projects. But I managed to find some 7.5K and 15K resistors to do this with that I had enough of, because you need quite a few of them. You need let's see, you need 9. I think you need 9 of the 2R, and you need 7 of the R. Would that be right? Yeah. Right. So yeah. So you arrange them in this layout, and at one end you're going to have your V out. So this, in my case, this is going to go to some speakers. So just to look at what's going on with the ports that I was talking about before, digital pins 0 through 7, that's 8 pins, they all happen to be in one port, and you can probably read through the whole of this page here. Just search for Arduino ports or something like that, port manipulation, and you can see a little bit more info about how this works. But basically, a port is a set of pins, and there's a port called D which maps to pins 0 through to 7, and this lets you do stuff like setting all of the pins or unsetting all of the pins of that port in one go, just by writing a single number to that port. So there's probably an example down here somewhere. So here's an example here. So you could put in your Arduino program port D, and this is a special variable. you can set that to be equal to, well, you can just set it to any number up to 255, but what they're doing here to explain this a little bit clearer is they're using the binary format for this number. So this is pins 7, 6, 5, and 3 are being set, and all of the other pins will be unset. And this is very quick. It's a very quick operation. It's much quicker than doing digital write to set pins individually. So that's what I'm going to do in my program to set the value of each audio sample as it's read. So we're going to read an audio sample, which is going to be an 8-bit number, from the file on the micro SD card, and then we're just going to set it directly onto port D, which is going to be these 8 pins. And then it's immediately going to take effect. So the nice thing about this resistor ladder thing is that it's apart from being quite easy to make, it's very, very fast to act. So there's no complicated logic or microcontrollers working. It's just a plain old analog sort of setup. So what shall we look at now? I suppose oh yeah, you'll need to prepare your file so that it's an 8-bit mono, preferably mono audio file. And in my case, I also wanted to make it a very low sample rate so that I didn't exceed the value or the data transmission rate of 115 kilobits per second, which is as much as I've tried with the these laser transmitter receiver things. So to show a little bit of the reasoning behind what comes next, 115 kilobits per second is that many bits per second. So if we divide that by 8, we find that we can transmit 14,000 bytes per second. And if one audio sample is 1 byte, that means we can have a sample rate of 14,400 samples per second. So that's 14,400 hertz audio. Hopefully this is making sense, but we'll have a look at it in Audacity, which shows us a graphical view, which might make it a little bit easier to understand. But the reason I'm choosing 14.4 hertz as my audio sample rate is because of what I just said. I don't want to exceed 115 kilobits per second. So where is my other... Okay, so this is my file that I'm going to use, or I'm going to convert to put onto the SD card. And where's my... Okay, so should be there. Yep. So this file is a bit like an MP3. It's a compressed audio file at the moment. And this one, fortunately, is copyright free, so I shouldn't have any problems with copyright violations or anything. So anyway, that's the song there, and Audacity doesn't actually read that song or read that file, or it doesn't read MP3s as well. So on Linux, what I do to change it to a wave, which I need to do for the next step, is I just use FFmpeg, and so I convert it to a wave like that. So this is much larger. You can see it's uncompressed now, but it's exactly the same result. And if we do FFmpeg, if you do FFmpeg -I and then the file name without any destination, it will tell you what format and video format and stuff that file is made from. So we can see we've ended up with a 44 kilohertz stereo signed 16-bit file, and this is 1,411 kilobits per second, which is way too much for us to be sending through the laser transmission thing. So the way I have been converting these, once I've figured out how to do it, is using the, what is this thing called? Sound Exchange. Yeah, this is a great little utility. So Windows users, obviously, I don't think you'll be able to. I don't know. There might be a Win32 port of this or not. I don't know. So I do fade wave as the input, and I need to change it to one channel, so that's mono. And I want the rate to be 14 kilohertz, and I want the bits to be 8 bits for my output file, and then the output file I'm going to call fade mono. And you can just do that. If you just do that, it'll take, I think, probably the left channel of that audio, the incoming audio. And I discovered something in my Googling around that if you do remix hyphen like that, oops, is this on the screen? Hopefully that was on the screen, but if it wasn't, it should be now. If you do remix hyphen, I think that's going to mix both left and right channels into the mono channel that results. So now we have a much smaller file. So this is the fade mono that we saw just before that I already have on the SD card. And this is 3.7 meg. And it doesn't sound as good. Although I guess when you're watching a YouTube video, might sound about the same actually. But not to make excuses or anything, but the audio that we get out of our Arduino is really quite terrible. But just keep in mind that we're not actually playing this high quality file to begin with. So so yeah, it's now if we check that fade mono just to see what kind of format we got, to double check. So now we can see we have 14,000 hertz mono unsigned 8-bit values. So if you are using Windows, you may not be able to do that. Another way you can do it is to use Audacity, which is a free. Okay. So you'll still need to convert it from MP3 or whatever you have to a wave. I'm not sure how you can do that on Windows. There's probably plenty of utilities that can do that for you. But once you've got your high quality wave file, you can open it with Audacity, and then you can do tracks, stereo track to mono, and then you can do project rate to, I think you can type in here. So I'm going to type in 144, and that should work like that. And if it doesn't work, you can also do resample or something. You can resample at 14400 as well. So I'll just do that to show you something else that's quite useful to illustrate what's going on here. So resample that at 14.4, and now when we play it, like I say, you may not be able to tell the difference in the YouTube video, but it's a fair bit lower quality audio. So now let's look at the beginning of this file and zoom in. I'm going to zoom right in. So here we can see each of those notes being played. And if we zoom right into the beginning again, where is it? Okay. So we can see some values. Alright, so when we zoom right in, we're actually showing each one of these audio samples as a dot. So you can see them sort of going up and down in a wave sort of a fashion, strangely enough. And that's how the audio is made up. Now I wanted to look at about here. Okay. Doesn't really show it too well, but so what we have here is, if you can imagine each one of these dots is a number between 0 and 255, because we're using 8-bit values, right? So this right in the middle is going to be about 127, 128 or something, isn't it? And as it fluctuates up and down, we're going to see numbers closer going to 0 or up to 255. And if we look at this file that we got as a result of converting to 8-bit audio, and we look at that with a hex editor like this, we'll see a little bit of header information at the beginning. This is just the standard wave header, and when we play the audio later, we'll actually be able to hear what that sounds like when we play it. It just sounds like a kind of noise at the beginning. But after that, let's go down here a little bit. Now we see a whole lot of numbers, 808080. So each one of these bytes in here is one of those samples that we saw in Audacity, which is gone there. So each one of these dots is one of these bytes, and you can see 80 is exactly, if it's unsigned 8-bit, it's 128, which is kind of what we expect. It should be right in the middle, and goes on for quite a while like that. 7F is 127. So basically nothing's really changing, and that's what we see here on the visual view in the background. And if we scroll down a bit, then we start to get into some actual music, which is this kind of stuff here. So when the values are fluctuating more than just one byte, one number, then that's what it looks like there. So our Arduino program is just going to read out one of these bytes and send it to the port, and it's just going to do that over and over and over until it gets to the end of the file. Alright, so you probably want to hear what this sounds like, right? So to save this, once you've set the project rate, at the bottom, and do this, where is it, stereo track to mono and stuff, you can export audio, and then you'll need to select other uncompressed files, and it's already selected. Okay, so other uncompressed files, and then in options you'll need to say unsigned 8-bit PCM. So there should be an option for that. The header type doesn't really matter, because it's only going to play a little bit of noise at the beginning of the file anyway. Anyway, so that's how you would export using Audacity instead of SOX. Let's just leave it open for now. Alright, so we want to hear what this sounds like, right? So over here I have my resistor ladder. Doesn't look quite as neat and tidy as the one in the Instructables photos, but it should be functionally fairly equivalent. I'm not sure how much the lengths of wire here is going to affect the quality of the sound, but yeah, it sounds pretty bad, so it could be that the wire is affecting it a fair bit. Alright, I've connected everything up now. The pins 0 through 7 just go straight onto each of those resistors, and then there's a ground that goes over there to the ground there, and then I'm left with another I guess you could call it ground and a positive, but it doesn't really matter with audio either way, because all it's doing is moving the coils in the speaker one way or the other. So the only difference in switching them round would give it the effect as if you're standing on the other side of the speaker. So it doesn't really matter. So I'm going to connect these up to the speakers from my computer amplifier, desktop computer speakers, but I just remembered that we haven't actually changed the program to make this work. So if I come back over to this dump file program, which was doing, what was this doing? Oh yes, it's dumping the text file. Okay, so we don't want to dump the text file, we want to dump the called fade mono. Fade is just the name of that song, by the way. So It's not actually fading sound or anything. So this time I'm going to try opening the WAV file, and instead of writing it to the serial monitor, we're going to do that port D thing, so that we just set port D, which is going to be the 8 bits along here, is going to be given the value of whatever byte we read from the SD card's file. Right. Whoops. So let's upload that. So I might just open the serial monitor. There's nothing to look at, hopefully. Okay, so it should be running now. And with these, so with these plugs here, the base terminal, the one at the base, is going to be the common terminal, or your ground you might call it, I suppose. And then the other two at the outside are the left and right channels of audio. So you'll need to put one of these onto the base. So that's, one of them is going to go there, and the other connection is going to go to one of the other two. So I'll just see if I can hold these on like this. Come here. And hopefully... Ooh, doesn't that sound great? So I can do left. Yeah, that's left and right. And it's going too fast, isn't it? Alright, so pretty soon I got sick of holding it on like that, but I just wanted to show you that that's how you can do that. So I made a little plug so I don't have to keep holding it. So I just cut one of these connections to have bring out the wires from inside, and then the one that has no color on it I'm assuming is the common, so that's what I used to do this. So I'll just plug this in here in place of that one, and then I won't have to keep holding it, because it's very awkward to hold. Alright, so it's too fast, and that's kind of a good sign, because it means that... oh jeez, shut up. That's kind of a good sign because it means that we can read data from the SD card fast enough to play the audio. If it wasn't fast enough, we might have to do some other method of reading, and there is a faster way we can do this. So what we're doing at the moment is we're checking if there's a byte available, and we're doing data file read. That will be 1 byte. So every byte we read, we're going through this loop. But if you do need to read something faster, I found that there's a function in this SD card library. You could do read, and then you'll give it a buffer. So you'd need a buffer of bytes, and then however many bytes you wanted to read into that buffer, and that's much faster. But unfortunately we don't need to do that. But what we do need to do to make that music sound a little bit more sensible is to slow it down. And I tried doing a few things like this. And this is, well, let's try it, shall we? Can you hear that? It's super slow. So we could try this. Microseconds. Let's try one. Actually, let's try, I think 10 microseconds was kind of reasonable. Still too fast. That's better. I found that you couldn't really get... God, it's horrible. I couldn't really get a very close match to the original speed by using delay microseconds. Somewhere around 18, 19 or something was a good match. So another method I tried was to do something like this. So instead of using delay microseconds, so the problem with delay microseconds is that it was like 18 was too fast and 19 was too slow or something. There wasn't enough granularity in the numbers. So one thing I tried was this. You just go around and around in a loop doing a no-op. So that the no-op is one instruction cycle or one cycle, and then the loop itself is going to take a few instructions to process as well. Now you may be saying, well, why don't you just do that without the no-op? And I found that didn't work. It just sort of gets optimized away. So you need to have a no-op in there for the compiler to actually pay attention to what you're trying to do. This worked out fairly reasonably, and I found that the value of 68 gave me fairly close to the speed of the original song. Oh, it sounds awful. It sounds worse than it did before. Found that actually taking some of these out gave a better sound. This one in particular. I'm just going to leave that one out. That's actually better. Oh, no, it's not. And the ones up here, the least significant bits, a lot of these really don't seem to make much difference at all. So I'm not sure what's up with that. See, I can take all of these top three out. Oh. Maybe not. Well, it's a bit of a weird thing how this works. So anyway, this is probably the best result I've had so far with this 68 no-ops. Another thing you could do, if you wanted to get it really precise, is just do a whole bunch of no-ops like that until you get to however many cycles it needs to slow down by. And I tried that, but it got to more than about it was over almost 300 of those it took to do it, so it just became a bit silly. So I decided to use a loop instead. So somewhere around 68 of this loop seems to match it up fairly well to the original speed. So that's about all I wanted to look at in this video. I will just look at one other thing though, and that is I noticed in the Instructables page that they are putting some capacitors and stuff on here and using a proper amplifier and things. I couldn't be bothered with that, but I think I'd just try putting some caps over the... Oh, this isn't going to work. Hang on a minute. Okay, sorry. Yeah, I forgot about that. For some reason when I hook it up to my computer's sound system, putting a capacitor over the outputs there just makes it stop completely. But when I was doing this earlier with my headphones, putting a capacitor over the output sort of rounded the sound off a little bit. It didn't make it better, it just sort of made it sound like it was muffled a little bit, like coming from the room next door kind of sound. So I'm not really expecting to get any better sound than what we just got from this, unfortunately. It does sound pretty terrible. But this will be something interesting to try, sending this audio data from here on one Arduino, using the laser transmitter receiver onto another one, and see if we can transmit some audio just using pure light. So we'll do that next time. See ya.